Welcome to the Urban Herald. Today, as part of the team, we're embarking on what I think is one of the most essential analyses of our time. We're not just skimming recent AI headlines.
No, not at all.
We are tracing the complete 82-year journey of artificial intelligence.
That's right. Our mission today is really to give you the full context. We are going all the way back to 1943 when this whole idea was, just abstract math.
And bringing it all the way up to today, to 2025, with these incredibly sophisticated generative and agentic systems that are, frankly, restructuring how global companies work.
Exactly.
And the history here, it's anything but a straight line. It's full of these revolutions and, retreats. By putting all this material together, we're hoping to offer you a kind of comprehensive shortcut to understanding the key turning points, the cycles of intense optimism, and then these brutal disappointments.
Yeah.
What we now call the AI winters.
And most importantly, the foundational breakthroughs that actually define the tools you're probably using today. And if we could frame this entire, 82-year history around a single idea, it would be this. Meaningful progress in AI has always required the precise, simultaneous convergence of three things.
Right.
Algorithmic innovation, computational resources, and massive data sets. When one of those three lags behind, progress just stalls.
So we're going to walk you through exactly when and how that convergence happened.
And when it didn't, which is just as important, so it plunged the field into winter.
Okay, let's start this journey then. Let's go back before the digital age to 1943.
Right.
The conceptual birthplace of artificial neural networks. It didn't involve transistors or silicon. It was pure abstract mathematics applied to, of all things, neurobiology.
Yeah, the foundation here lies in the work of a neurophysiologist, Warren McCulloch, and a mathematician, Walter Pitts. Their paper, A Logical Calculus of the Ideas Immanent in Nervous Activity, it really created the first computational mathematical model of a neural network.
And what's so pivotal about their work, the really profound realization they had.
It was this true aha moment, wasn't it?
It was. They took these early ideas about computation from people like Alan Turing, and they showed that a network of simple, connected elements, which they just modeled as on or off switches, could, in theory, perform any logical function.
And that realization just stripped away all the biological messiness of the brain.
Right.
It suggested that intelligence, no matter how complex it seems, could be described in pure, abstract mathematical terms.
Which means it could potentially be computational.
Exactly. It became the essential blueprint for everything that followed, even though it was, mostly just theory at the time.
So then, moving into the 1950s, the field starts to get a bit more formal. In 1950, Alan Turing, in his paper Computing Machinery and Intelligence, gives us the standard we still kind of use to measure machine intelligence, the Turing test.
And the power of the Turing test was just its practicality. It completely sidestepped the impossible philosophical questions about consciousness or whether a machine truly thinks.
It just focused on behavior.
Just observable, external behavior. If a human interrogator, typing back and forth, couldn't reliably tell the machine apart from a human, then for all practical purposes, the machine should be considered intelligent.
And the test is still so relevant. No system has passed the full rigorous test, but the fluency of today's large language models.
Oh, it's absolutely reignited the debate, hasn't it, about whether parts of that benchmark have been met.
For sure. And then comes the official christening of the field in 1956.
At the Dartmouth Conference, organized by John McCarthy, this event brought together all the pioneers, Marvin Minsky, Claude Shannon, and it's really seen as the founding moment. It's where McCarthy formally coined the term artificial intelligence.
And the enthusiasm at that conference was, you could almost call it reckless.
Oh, definitely.
They genuinely believed they were just a few years away from artificial general intelligence.
Their hypothesis was that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. That belief just drove everything.
So they had the theory, they had the optimism, and by the late 50s, we start to see the first practical systems.
Yeah, as early as 1951, the Ferranti Mark I machine at the University of Manchester was running some of the first AI programs.
Like checkers and chess.
Checkers from Christopher Strachey and a chess program from Dietrich Prince.
But the real, foresight into what would become the dominant idea of machine learning that came from Arthur Samuel at IBM.
Yes. Over a decade, from 52 to 62, he wrote this checkers program that showed a staggering ability to get better over time.
It wasn't just playing, it was learning.
It was learning from its own mistakes, It would evaluate the board, make a move, and then update its own internal weights based on whether that move led to a win or a loss.
And it actually got good enough to challenge a decent amateur player.
It did. And crucially, Samuel coined the term machine learning in 1959. He saw that computers could learn on their own and, amazingly, could even outplay the people who programmed them. That was just a revolutionary idea.
That concept, a system exceeding its programmer, that's really the DNA of all modern AI.
Absolutely.
And then 1958 was a huge year. We get two massive technical contributions. John McCarthy invents the Lisp programming language,
Which became the standard for AI for decades because it was so good at handling symbols and logic.
and Frank Rosenblatt develops the perceptron.
Right. Directly inspired by McCulloch and Pitts. This was an early single-layer artificial neural network. It was the first time that concept was made tangible.
And they demonstrated it using this enormous 5-ton IBM 704 vacuum tube mainframe.
And it could classify simple patterns. It was the first real attempt to mimic the brain with a computer.
Yeah.
And it really set the stage for decades of debate and controversy to come.
So moving into the 1960s, we enter what's often called the golden age of optimism. And this wasn't just, academic dreaming. It was fueled by huge government investment.
Indeed. The Defense Advanced Research Projects Agency, or DARPA, was just pouring millions of dollars into fundamental AI research.
Yeah. So people like Minsky, McCarthy, Simon, and Newell at places like MIT and Stanford.
They had basically a blank check. They could pursue these big blue sky questions about machine intelligence without any pressure to deliver a product right away. That freedom was critical.
And this era produced some really landmark systems, even with the primitive hardware they had. Joseph Weissenbaum creates ELIZA at MIT in 1964.
ELIZA, the first really famous chatbot.
And it was based on pretty simple pattern matching, right?
Very simple. It was designed to mimic a psychotherapist. So if you typed, "I feel sad," it was programmed to respond with something like, "Tell me more about why you feel sad."
So the interesting thing about ELIZA wasn't the tech itself, it was the psychological impact.
Exactly. People were deeply engaged by it.
Hmm.
Shockingly, they often thought it had real human emotions and understanding.
It really showed our human tendency to anthropomorphize, to see humanity in these systems.
We also saw the beginnings of the expert system concept, which would become huge later on. Work started on Dendril in '64 at Stanford.
And Dendril was a big step towards applied AI. It was an expert system designed to help chemists.
Right. It would analyze complex data from a mass spectrometer and then hypothesize what the molecular structure could be. It proved AI could handle specialized reasoning in a very narrow scientific field.
And then there was the push for embodied AI, which gave us Shaky the robot.
Developed at SRI, starting in 1966.
Shaky was just revolutionary because it brought so many different AI disciplines together in one place.
It really did. It was the world's first mobile intelligent robot. It had AI for logic, computer vision to see, navigation to move around.
And it could even understand simple natural language commands.
You can draw a straight line from Shaky to today's self-driving cars and drones. It's the foundational ancestor.
But despite all this momentum, all this investment, the field just hits a catastrophic roadblock in 1969.
The perceptron crisis.
Okay, we need to be very clear about what happened, what exactly triggered this crisis. It's often traced back to the book Perceptrons by Marvin Minsky and Seymour Papert.
That's right. The book was a devastating mathematical critique. They rigorously proved the limitations of single-layer neural networks like Rosenblatt's perceptron.
So they showed mathematically that these simple models could only solve problems that were, linearly separable.
Exactly.
And the classic example of a problem that isn't linearly separable is
the XOR function, exclusive OR. It's a problem that's trivially easy for a two-layer network to solve. But Minsky and Papert proved a single layer simply couldn't learn it. The decision boundary just can't be drawn with a single straight line.
So the technical point they were making was correct for those simple models.
Oh, it was mathematically sound. But the political and the funding impact was just disproportionate.
Right.
The book was widely interpreted, and you could argue Minsky deliberately pushed this interpretation as proof that neural networks in general were a computational dead end.
So this one technical limitation was blown up to mean the whole approach was flawed.
Exactly. And it caused this massive shift in funding.
Yeah.
All the money moved toward symbolic, logic-based AI, and it effectively just suffocated neural network research for more than a decade. It was the first great divergence.
And that led directly to the first AI winter, which we can date from about 1974 to 1980. The momentum just stopped.
It did. And this was a period of severe disappointment.
It wasn't just the perceptron critique, though. It was a broader failure of ambition hitting the wall of reality.
Absolutely. Researchers had promised human-level AI within years, but they were working with incredibly limited computing power, algorithms that just didn't scale, and almost no data.
The first big shot came from the UK.
The 1973 Lighthill Report, commissioned by the British Science Research Council, it was just a devastating critique. It basically said AI had failed to achieve its goals.
And the result was immediate.
Immediate and severe. The UK just drastically cut funding for AI research, and that pessimistic view quickly spread to the US.
At the same time, the US government's priorities were changing.
Right. The Mansfield Amendment in '69 had already said DARPA should only fund mission-oriented research. And by '73-74, that meant funding shifted away from open-ended academic questions toward very specific projects.
Like autonomous tanks.
Exactly. Not what is intelligence.
And the result was really tragic for the field long term. Funding dried up, researchers left.
And a lot of institutional knowledge, a lot of wisdom from the '60s was just lost or abandoned.
But as the funding pressure grew, necessity kind of drove innovation in a different direction.
It did. It led to the expert system boom in the 1980s. This was the field's first real, genuine commercial success.
This was a resurgence driven by symbolic AI programs designed to mimic human experts, but only in very narrow, very constrained domains.
Right. These systems had two main parts. You had the knowledge base.
Which is where you'd manually encode all the facts and rules from a human expert.
Exactly. And then you had the inference engine, which was the logical part that would apply reasoning to that knowledge base to come to a conclusion.
The big commercial turning point came in 1980 with a system called R1, or XCON.
Developed at Carnegie Mellon for Digital Equipment Corporation. Its job was to configure these hugely complex computer systems, a task that normally required human experts and was prone to expensive errors.
And the numbers, they tell the story.
They absolutely do. R1 was astonishingly successful. By 1986, it was saving DEC an estimated $40 million a year.
Wow, $40 million.
Annually. It just proved, without a doubt, that AI could deliver a measurable commercial ROI.
And that was the signal the market was waiting for.
It was. By 1985, corporations were spending over $1 billion on AI, mostly on their own in-house expert systems departments.
You saw them in medical diagnosis, like NYCIN, financial planning on Wall Street. They were everywhere. The 80s were AI's shift from theory to a specialized, practical, and profitable reality.
But that boom, while it was commercially vibrant, was built on really brittle foundations. And history, well, it proved to be cyclical. The flaws in those systems are what triggered the second AI winter.
Roughly from 1987 to 1993.
Right. And the failure was really twofold. It was about hardware, and it was about methodology.
The crash started with the hardware, with the collapse of the Lisp machine market in '87.
Yeah, these were expensive, custom-built machines designed specifically to run AI software. And they just became obsolete almost overnight because general-purpose computers like Sun workstations and early PCs got so much better, so much faster.
So relying on custom hardware was a fatal mistake.
It was. And the second problem was the methodology itself. Expert systems were great in their little boxes, but they suffered from what's called the knowledge acquisition bottleneck.
Meaning it was incredibly difficult and time-consuming to get the rules out of a human expert's head and into the computer.
Exactly. And even worse, the systems couldn't learn from experience. You had to manually update them all the time, which was incredibly expensive and difficult. They were brittle.
And once again, government funding followed the industry trend.
In 1988, the Strategic Computing Initiative, a major U.S. defense program, just canceled all new spending on AI. That pretty much sealed the deal for that generation.
But, and this is so crucial for our deep dive, while the public-facing symbolic AI industry was collapsing.
A quiet, profound revolution was happening in the background. In that corner that everyone had dismissed. Neural networks.
This was the neural network renaissance, and it was driven by the popularization of backpropagation.
Yes, in 1986, David Rumelhart, Jeffrey Hinton, and Ronald Williams published this seminal paper that really detailed the algorithm.
And this was the breakthrough that solved the technical problem from the perceptron crisis.
It was. The challenge was always how to efficiently train a network with multiple layers. With many layers, you have to figure out how to assign blame for an error, back to potentially billions of individual weights, many steps away from the final output.
And backpropagation made that possible using the chain rule from calculus.
Pretty much. The algorithm calculates the gradient, basically how much each specific weight contributed to the final error, and then it propagates that error signal backward through the network, layer by layer.
So it allows the network to systematically adjust every single connection to reduce future errors.
It's this highly sophisticated automatic tuning mechanism. There's a great analogy that training a network with backpropagation is akin to adjusting the knob on a radio to catch the right signal.
Except there are billions of knobs, and each one needs millions of tiny adjustments.
Exactly. This technique finally allowed networks to automatically learn the complex, nonlinear functions that Minsky and Papert had proved single-layer perceptrons never could. It laid the entire blueprint for modern deep learning.
And that academic breakthrough, born in the quiet of the AI winter, is still the absolute backbone of modern AI today.
It is.
That foundation then gets built upon architecturally in the late 80s and 90s. In computer vision, Yann LeCun and his colleagues started applying backpropagation to convolutional neural networks, or CNNs.
Which led to the breakthrough system LeNet-5, published in 1998.
LeNet-5 pioneered concepts that are still standard in image processing today.
Oh yeah, things like shared weights, where the same feature detector is used across the whole image, pooling layers to shrink the data down, and local receptive fields. It was an architecture designed specifically for the structure of images.
And it had immediate concrete success in a high-stakes commercial setting.
It did. LeNet was used to read handwritten zip codes for the U.S. Postal Service and was even adapted to process checks in ATMs.
We're talking about code from the 1990s that was so reliable it was embedded in critical financial infrastructure.
At the same time, for sequential data like text or speech, researchers were stuck on the vanishing gradient problem.
Right. In standard recurrent neural networks, or RNNs, the error signal would just shrink as it flowed through a long sequence, making it impossible to learn long-range connections.
The solution to this was maybe the most important quiet innovation of that whole era. In 1997, Sepp Hochreiter and Jürgen Schmidhuber introduced long short-term memory, or LSTMs.
And LSTM solved the vanishing gradient problem with a really genius modification.
It was. They introduced a dedicated memory cell and these highly controlled gating mechanisms.
The forget gate, input gate, and output gate.
Exactly. The forget gate decides what old information is no longer relevant. The input gate decides what new information to store. And the output gate decides what part of that memory to use for the current prediction.
So it gave the network control over its own memory.
And that allowed the error to flow back over thousands of time steps, finally letting the networks learn long-term dependencies.
And what's amazing is the delayed but massive impact of this. This architecture, perfected during the obscurity of the second AI winter.
By 2017, it was everywhere. It was powering Facebook's machine translation, Apple's QuickType keyboard on 1 billion devices, and Amazon's Alexa. The seed planted in the winter grew into the most pervasive form of AI.
Which brings us to the period where those three critical ingredients, algorithms, compute, and data, finally truly aligned.
The deep learning revolution between 2006 and 2012.
Before 2006, networks were still pretty shallow because it was so hard to train the very deep ones.
Right. In 2006, Geoffrey Hinton and his colleagues showed you could effectively pre-train deep networks using unsupervised learning first, which helped get the weights into a good starting position before the final supervised fine-tuning.
But the data scale, that was arguably the biggest game changer.
Oh, absolutely. Fei Li and her team creating ImageNet starting in 2007.
And ImageNet was a watershed data set just because of its sheer size and variety.
Over 14 million high-resolution, labeled images across 22,000 categories. And crucially, they used Amazon Mechanical Turk to do the labeling, which showed you could scale human annotation cheaply.
So ImageNet became the ultimate testbed, the ImageNet Challenge, or ILSVRC, and it proved that data scale was now the most important variable.
But the data and the algorithms were useless without the third piece of the puzzle. Compute power.
The rise of general-purpose GPU computing.
Exactly. NVIDIA's CUDA platform, launched around 2006-2007, was the engine for the revolution.
And why were GPUs, which were made for video games, so perfect for deep learning?
Because training a neural network is just billions and billions of matrix multiplications. It's an inherently parallel task.
Which is exactly what GPUs are designed for.
Right. CPUs do things one by one. GPUs do thousands of things at once. They were orders of magnitude faster for the specific math AI needed. That computational power unlocked the ability to go really deep.
And the moment of truth, the complete convergence of all three factors, came on September 30th, 2012.
AlexNet.
Alex Krizhevsky, Ilya Sutskever, and Jeffrey Hinton submitted AlexNet, a deep CNN with 60 million parameters, to the ImageNet challenge. And the results.
They weren't just a win. They were a complete annihilation of the competition.
AlexNet achieved a top 5 error rate of 15.3%. The runner-up, which was still using older handcrafted methods, was more than 10 percentage points worse.
It was just irrefutable proof. It showed that deep neural networks, given enough data and compute, just dramatically outperformed every other approach. It was the death of handcrafted features.
And it convinced every major tech company that deep learning was the future.
Absolutely. And AlexNet's specific innovations were also key. Using the ReLU activation function for faster training, introducing dropout to prevent overfitting, and pioneering the use of multiple GPUs to handle the load, that one event changed everything.
So the deep learning paradigm was set, but the next big leap required a totally new architecture, a move away from the LSTMs and RNNs.
That shift arrived in 2017 with the transformer architecture.
From the paper, Attention is All You Need, by a team at Google. And it got rid of recurrence and convolutions entirely, relying only on self-attention.
Which was revolutionary.
Yeah.
LSTMs had to process words one by one sequentially, which was a bottleneck. The transformer, through self-attention, could process the entire sentence all at once in parallel.
And that made it dramatically faster to train and feasible to scale up to the size of the entire internet.
Right, and the self-attention mechanism itself. Yeah. It calculates the relationship between every word in a sentence and every other word. It dynamically weighs the importance of other words when it's processing a specific word.
So if it sees the word bank, it can immediately tell if it should pay more attention to river or to money based on the context.
Exactly. And the multi-head attention just amplified this, letting the model look at different kinds of relationships, say grammar versus meaning all at the same time.
And this new architecture immediately split the field into two major branches.
First, understanding. In 2018, Google introduced BERT, which stands for bidirectional encoder representations from transformers. It used an encoder-only structure to deeply understand language context by reading text in both directions at once.
And BERT's impact on language benchmarks was just unprecedented. By 2020, almost every single English query on Google search was being processed by a BERT model.
Meanwhile, OpenAI took the generative path with the GPT series, using a decoder-only structure focused on predicting the next word in a sequence. GPT-3 from 2020 was just colossal, 175 billion parameters.
And the most profound thing about GPT-3 was its ability for few-shot learning?
Right. You could give it a couple of examples of a task in the prompt, and it could just do it. Translation, reasoning, writing, all without any additional fine-tuning. It was a huge leap in flexibility.
Beyond just language, this architecture proved it could tackle massive scientific challenges.
DeepMind's AlphaFold 2 is the perfect example. In 2020, it effectively solved the 50-year-old protein folding problem.
And just for context, figuring out a protein's 3D structure used to take months or years in the lab and cost a fortune.
AlphaFold 2 changed all that. It used a novel architecture called the evoformer and achieved accuracy scores that the experts themselves said meant the problem was largely solved.
And the data release was just as important as the model.
Absolutely. By 2024, AlphaFold had predicted and released over 200 million protein structures for free. It's one of the biggest contributions to biology since the Human Genome Project.
And AlphaFold 3 in 2024 took it even further, predicting how multiple molecules interact, the key to accelerating drug design.
All of these breakthroughs culminated in the generative AI explosion, starting in 2022.
And the real inflection point for the public was ChatGPT in November 2022.
Its growth was just explosive. It reached 100 million users in 2 months, faster than any other app in history. And that was because it was easy. It democratized powerful AI through a simple conversational interface.
And a key part of its success was the training method, reinforcement learning from human feedback, or RLHF.
Right. This is where you bring humans into the loop. You have them rank different model outputs, use that preference data to train a separate reward model, and then use that to fine-tune the main language model.
So you're aligning the model with complex human values, not just predicting the next word.
Exactly. And the pace of improvement was just relentless. GPT-4 in 2023 showed these huge jumps in reasoning.
By 2025, the models had evolved even further. GPT-5 introduced multiple reasoning modes.
Right, like Instant Thinking Pro and Auto. These aren't just speed settings. They let you trade latency for computational depth. Thinking mode might use chain of thought reasoning, while Instant is for quick conversation.
And then GPT 5.1 added personality customization, letting you tailor the AI's tone and style.
Generative AI also exploded into multimodality. DALL-E integrated into ChatGPT, generating high-quality images from just text.
And it shows a deep conceptual understanding. The source material has that great example, an illustration of an avocado in a therapist's chair being counseled by a spoon.
It's perfect. It has to understand three totally separate concepts, avocado, spoon, therapy, and synthesize them into one coherent image. It's remarkable.
So as we arrive in the present day, 2025, the focus has shifted again from just generating things to autonomous action. We're in the era of agentic AI.
And agentic systems are fundamentally different. They're defined by their ability to pursue complex, multi-step goals with minimal human supervision.
They can adapt to unexpected things and coordinate actions across different software platforms.
The technical leap for this is huge. It's not just a prompt and response model anymore.
It needs real planning capabilities, right?
Yeah.
To break down a big goal into smaller executable steps.
Exactly. It also needs robust memory systems, both long-term and short-term, to keep track of a project over days. And critically, it needs resilient error handling.
So if something goes wrong, like an API call fails, it can recover and replan on its own instead of just giving up.
Right. The applications are transformative handling complex customer service issues, autonomously debugging software, managing business automation.
At the same time, multimodal systems are becoming seamless. They no longer treat text, images, and audio as separate things.
And healthcare is the most compelling example of this. You have multimodal systems combining medical images, health records, lab results, and doctor's notes to give a truly holistic diagnostic insight.
All of this rapid acceleration, though, has made governance an urgent issue.
Absolutely. Organizations everywhere have had to quickly create and implement AI governance frameworks.
The EU's AI Act really set the global standard here.
It did. It established these comprehensive risk-based rules. So high-risk applications, like in hiring or credit scoring, face really strict requirements for transparency and human oversight.
In response, corporations have had to create things like internal AI ethics committees, rigorous testing protocols for bias.
And financial services and healthcare are leading the way just because the stakes are so high.
And if we look at the broader impact, pharmaceuticals is one of the most promising areas.
It's critical. The traditional drug discovery pipeline is 10 to 15 years long. By using AI to analyze molecules and predict interactions, leveraging insights from things like AlphaFold, it's projected to shave several years off that process.
Okay, to really grasp the complexity of modern AI, let's do a quick deep dive into one of its hardest applications: autonomous vehicles. This is embodied AI in the real world.
And the difficulty is that any single sensor can fail. Light, rain, fog. So you need sensor fusion combining data from multiple different sensors in real time.
Okay, so let's break down the sensors. You have cameras. They provide that rich, high-resolution visual information.
Right, for reading signs, seeing traffic light colors, lane markings, subtle pedestrian movements. But they fail in bad light or heavy glare, and they can't measure depth directly.
So that's where LiDAR comes in, light detection and ranging.
Exactly. LiDAR sends out millions of laser pulses to create a super precise 3D map of the environment. It gives you accurate distance, works well in the dark.
But it's expensive and can struggle in heavy rain or snow.
Which is why you also have radar. Radar uses electromagnetic waves. Its strength is that it can see through bad weather fog, rain, snow. It provides robust object detection, even if the resolution isn't as good.
So sensor fusion is constantly taking all this data, some of it conflicting, and piecing it together into one coherent picture of the world.
And the AI processing needed to turn that data into driving commands is just immense.
At the core, you have deep convolutional neural networks, the legacy of AlexNet, handling object detection.
They're trained on massive data sets to identify and classify everything at once. Cars, pedestrians, signs, debris.
But driving is more than just knowing what's there. It's understanding the scene and predicting movement.
That's where semantic segmentation comes in. This is where the AI classifies every single pixel in the image. It labels the sky, the sidewalk, the drivable road surface. It creates a detailed, real-time map of the drivable space.
And then the final step is path planning.
Right. It uses that complete understanding of the scene to navigate safely, obey the rules, and generate the precise commands for steering, accelerating, and braking.
But huge challenges remain.
Oh, definitely. Ensuring reliability in all weather conditions. Handling those rare edge cases that weren't in the training data.
And the ethical question, the trolley problem. How do you program a car to make a choice in an unavoidable accident? That's a governance problem for autonomous action that we are still very much grappling with.
So reflecting on this entire 82-year journey, from that abstract McCulloch-Pitts model to today's agentic systems, you really do see these powerful, enduring patterns.
The most critical lesson, like we said at the start, is this absolute necessity of convergence.
AI progress was never a straight line. It always required that synchronized alignment of algorithmic innovation, computational resources, and massive data sets.
Right. Backpropagation was just a theory until GPUs could actually train it. AlexNet only happened because of ImageNet and CUDA.
And transformers needed the whole web as data and immense compute power to scale up to create something like GPT-3.
And we have to remember the lessons from the AI winters. Those setbacks were crucial development periods.
They were. They forced the field to abandon the grandiose claims, to focus on achievable problems, and critically, to quietly incubate the foundational breakthroughs, like backpropagation and LSTMs, that powered the next stage.
Those quiet breakthroughs, the ones that happen when everyone is pessimistic, are arguably the most important data points in this whole story.
Yeah, the LSTMs of 1997, the backpropagation renaissance of 86. They were born when funding was scarce and public interest was low.
So the 2025 reality is breathtaking. We have agentic and multimodal systems augmenting human capabilities everywhere. But it's also vital to remember we are still in the realm of narrow AI.
We are a long way from human-level general intelligence, or AGI. And the focus now is heavily on safety, fairness, and governance.
The source material also points to the next chapters, the future research directions. Things like continual learning systems.
Systems that can learn new things without catastrophically forgetting what they already know.
And huge pressure for more efficient, less energy-intensive architectures as the climate cost of training these giant models becomes a real issue.
And critically, the sustained push beyond just pattern recognition toward true general-purpose reasoning and planning. That's what will define the next decade of innovation.
So as members of the Urban Herald team, having analyzed this whole cyclical history of hope and collapse, we want to leave you with one final provocative thought.
Right. Given this deep, undeniable cyclical nature of AI history, where the most transformative breakthroughs, as we've seen, often happen quietly during the AI winters, far from the spotlight.
The question is, what foundational research is being conducted today, maybe in some niche, underfunded corner of academia, that will be recognized as the transformative technology of 2040?
Think about it. What research project, maybe on meta-learning or symbolic reasoning or neuromorphic hardware, something that doesn't generate text or images right now, is going to power the next great wave?
What is our modern-day perceptron or LSTM just waiting silently for its moment of convergence?
Thank you for joining the Urban Herald team for this deep dive into the complete 82-year evolution of artificial intelligence.
We'll see you next time.